Okay, so this is something that's like a pain to calculate, but it's something that um, is really simple to define. So we're coming back to orthogonal projections, and this is going to be a fairly big tool for us in the coming days, but I just want to make sure that we got the basics of it down. So back when we were dealing with a dot product, what we did is we had some vector v, and we had another vector u, and we said what would happen if I dropped this down into here, and then I said, well, I would get a vector that looks like this that's in the same direction as v, but it has the correct magnitude so that it creates the right angle there, and it's basically the shadow of u onto v. So in R2, back in ACalc, this would be the projection of u onto v. Okay, so basically, since I have an induced inner product, I can do this as well. So let's let u and v be elements of some v, which is now not a vector space, but an inner product space. We've stepped up, and v right now cannot be the zero vector, because doing this doesn't make sense if I'm projecting onto something that has no magnitude. Okay, so then we're going to define this same thing, the projection of u onto v is going to be the inner product of u and v over, so that one's the v, right, over the inner product of v with itself times v, because this is a vector, right? This thing is an element of v, right? So this is a vector that has the same direction as the v vector, whatever that means in terms of our stuff. But see, now because I'm working this with an inner product, these vectors can be things like matrices, and they can be things like what do you call it, polynomials, and can be continuous functions on an interval. So there you go, 2.5 minutes, shortest video to date, and that's what we're doing. All right, so we'll look at these later on in class.